All right, welcome to the last lesson of our sinusoidal functions unit. This is problem solving using sine functions, so word problems. A group of students is tracking a friend, Dawson, who is riding a Ferris wheel. They know that Dawson reaches the maximum height of 11 meters at 10 seconds. I'm just going to highlight this. So our maximum is 11 meters. It happens at 10 seconds and reaches the minimum height of 1 meter after 55 seconds. We want to develop three equations, sine function equations that models Dawson's height above the ground. So the first thing we need to do, we're just going to picture the Ferris wheel. So it has a maximum of 11 meters and it happens there at 10 seconds. And it reaches the minimum after 55 seconds. Okay, so from maximum to minimum is 45 seconds. And then from minimum back up to maximum, another 45 seconds. So we can determine that the period equals 90 seconds. Okay, as for the other information, to find our amplitude, we have the maximum minus the minimum divided by 2. So the amplitude happens at 5 meters. To get our equation of the axis, it's the maximum plus the minimum divided by 2, which is at 6 meters. And the k value for our equations, 360 divided by our period of 90, which is 4. Okay, so equation number one, it wants three equations. Because we know when the maximum occurs, we're going to work with cos for the first one. So our amp is 5, our k value, is 4, and it reaches the maximum for the first time at 10 seconds. And I'll just show you here. So let's see is 6. So d equals 10 because it's the first time it reaches the max. Okay, so we plug that into the equation, and the only thing that's changing here is the d value. Good. A second form of equation, I'm going to work with y equals positive sine x. Okay, and the parent function of positive sine x reaches the maximum at 91, but in this case it reaches the maximum at 1011. So so we can work with 1 over kx, plus d. We're finding the d value here. So we can work with half of our mapping rule to find the new x value. And we know that it has to equal 10. Okay, it's because the maximum happens at 10. So our k value is 4. We're going to plug in the original x value plus d, and we want it to equal 10. A quarter times 90 is 22.5 equals 10. So we isolate d. 10 minus 22.5 is negative 12.5. Okay, so that's when you're going from cos to sine, the only two things that change are the phase shift, so the d value, and the word from cos to sine. So this one will have an equation. The amplitude stays the same. We're changing it to a sine. The k value stays the same, but we are changing the phase shift. Okay, so that is equation 2. And then equation 3 we'll do in blue here. And we're going to work with negative sine x, because we know a minimum value. Okay, again, we want to find the d, so the parent function for negative sine is 90 negative 1, and we're trying to get it to 55 1, which is the first time that it reaches the minimum. So again, we have 1 over k, which is 1 over 4. We're plugging in the original 90, and this time it will equal 55. Okay, because again, we're moving from the parent function to the new function, so it moves from 90 to 55. So when we plug this in, 22.5 plus d equals 55. 55 minus 22.5 is 32.5. So the third equation, y equals negative 5. We're working with negative sign, so negative 5 sine 4 x minus 32.5 plus 6. Okay, so using half the mapping rule, we only used half because we're only looking for d to find out the new phase shift. How high above the ground is Dawson at 78 seconds? I'm going to use the first equation that we did in purple, the cos one. So it's talking about seconds, which represents the x values at 78. So we have 5 cos 4, and it wants 78 minus 10 plus 6. So we get 5 cos 78 minus 10 is 68 times 4 is 272. Okay, the cos of 272 multiplied by 5 and adding 6 gives us 6.2 meters. Okay, I'm not showing all the steps there. You can do it if you want. It's just bad math by using cos. Okay, the top of a flagpole sways back and forth in high winds. The top sways 10 centimeters to the right. So this will be your maximum. And 10 centimeters to the left. This will be your minimum. Of its resting position, and moves back and forth 240 times every minute. At t equals 0, the pole was momentarily at its resting position. So that means it's EOA at 0. So that means we're going to use y equals sine x. Determine the equation of the sine function that describes the distance the top of the pole is from its resting position in terms of time. Okay, so we have our a value, which is the maximum minus the minimum, divided by 2, which is 10. The c value, which is our maximum plus our minimum, divided by 2, which is 0. The k value, so first to do the k value, we need the period. So it happens 240 times every single minute. So 60 seconds divided by 240 times per minute is 0.25. Okay, so it sways back and forth every 0.25 seconds. So the k value is 360 divided by 0.25, which gives us a k value of 1,440. And now we can start filling in. So starting point is 0, 0. Starting point. And again, I know I mentioned it above, but because it's starting at the equation of axis, we will be using y equals sine x. Okay, so our final equation is y equals a value of 10. We're using sine. There's no phase shift, so we just put the k value in with the x, and there is not equation of axis change. If the wind speed decreases slightly such that the sway of the top of the pole is reduced by 20%, what is the new equation of the sine function? Assume the period stays the same. So all that's changing here is the maximum and the minimum. So it's reduced by 20%, which means that it is 80% of what it used to be. And 10 times 0.8 is 8. So that happens both ways. So the new max is 8, and the new min is -8. Okay. So this just means that our amplitude is now 8 instead of 10. So the new equation would just be 8 sine 1440x.